Variance. We want to talk about what variance is and why it's important. From a mathematical standpoint, variance is the average of the squares. Squares has an S in it. Squared differences, sorry, of the squared differences from the mean. Okay, so basically the difference from the mean means we take the average, we take the data, we make a difference, we subtract, and then we square all of them. And then it's the average of all that. Okay, that doesn't really tell you, okay, so what's it for, right? Okay, variance tells us how far the data spreads from the mean. Basically, how far from average do things get? If we're looking at toys, right? And we're looking at the production numbers, 6,500, 2,500, 5,700, 8,000, 3,800. They can calculate the variance to determine, like, how efficient are they? If you're manufacturing toys in a factory, high efficiency means you're making a high number of toys, about the same number every day. If it's all over the place, they're going to want to look at their processes and see if something's wrong. If something is too variable, it's not necessarily a good thing. So the variance tells us how far the data spreads from the mean. The higher the variance, the further the spread. Okay. Now there's no maximum variance. It's not like with probability where we went between 0 and 1. It wasn't like that. Variance can be between 0 and any number that exists ever. So there's no cap on that. It's not negative. But it can go from, I mean, theoretically, it could go from 0 to infinity. If your variance of 0, then all the numbers are the same. So, for example, let's say you are manufacturing toys, and every single day you manufacture 6,500 toys. You manufacture 6,500 on Monday, you manufacture 6,500 Tuesday, Wednesday, Thursday, Friday, etc., etc. Your variance would be 0 because there is no varying. You're exactly the same number every day. And the closer you are to 0, the closer your numbers are to being the same as each other. Does that make sense? Okay. All right, variance is symbolized by this right here. This is the Greek letter sigma. Okay, so sigma squared is the symbol for variance. It has to have the squared on it. If it doesn't have the squared, it's not variance. Okay. And we are going to calculate the variance of a population, and we're going to calculate the variance of a sample. And so we need to talk about the difference between a population and a sample. A population is every single possible piece of data. So every single possible member. If we wanted to do a study of this classroom, just this classroom, you guys would be the population. But if we wanted to do a study of the whole school, but we only used you, you'd be a sample. Okay? So the same group of people or the same group of data can be a population or a sample depending on your parameters for the whole study. But when you're talking about a population, you're using every single possible piece of data. Okay, so first we determine the mean of the data values. This is calculate the average. And then we subtract the mean from each piece of data. Now, when we're talking about the average of a population, we use this letter here, which is the Greek letter mu. Okay, so this is data minus average. And that, again, is a population. Okay, then we square each of those differences to determine the total of the results. So we take x minus mu and we square them. Then we add them all together and we divide them by how many numbers we used. So this is sum. We take the sum of all of the numbers. And so we have the sum of the data minus the average squared divided by the number of the population, like how many there were in the population. And that gives us the variance. Okay, so far. Now, the variance for a sample is slightly different than the variance of a population. Okay, and this is because the sample, remember, is like a representative of a population. So when you're taking and picking a sample, if you were actually conducting statistical research, you were going to try to choose a sample that most mimics the entire population. It's a representative of the population. However, having said that, it is not 100% accurate. Right? No matter how careful you are in your sample selection, you're never going to get the same results as if you were able to do a statistical analysis on the entire population. Okay? And so because of that, the differences are subtle. This S stands for variance of a sample. Okay, so S squared, sigma squared is variance of a population, S squared is variance of a sample. Then the difference here, you have X bar. This is still the average. And it's calculated the same as when you use mu, but we use X bar when it's a sample, just to indicate that this was a sample average and not a population average. That's really that is the only difference, is so that if somebody's looking at your work and you used X bar, they'll know it was a sample. And that's what that's called. It's called X bar because it has a bar over top of it. And then we take the total number and we subtract 1. So that's the only, that is really, as far as your calculation goes, that is your only difference between calculating the variance of a population versus calculating the variance of a sample. So it's the sample minus 1. But it does give us a slightly different result, because instead of dividing by, say, 10, we would be dividing by 9.
So sample number, not total number minus 1.
Yeah, however many people you used in your sample, which is the same thing as your total. It's just your total of your sample instead of your total of your population, if that makes sense. Okay. Calculating the variance. Let me go back a little bit. Calculating. If you use a table, it makes everything a million times easier than if you try to do it the long way. So we're going to do a table. Now what we're going to do is we're going to test exterior house paint to determine how long it retains its color. Why would we want to know the variance on this? Okay, you're going to advertise this paint. You're a company and you're making paint. You're going to advertise this paint, and when you put on the label, people want to know how long it's going to last. And so you put on the label, 5 years or whatever, let's just say. Well, paint that has more variance in the time that it lasts when they test it is going to be less reliable. A shorter variance means if you're saying the average time this paint lasts is 5 years, then your variance being really small means that they'll last, somewhere really close to 5 years. So you're more reliable. Whereas if you say it lasts on average 5 years, but you have a really huge variance, one person's going to grab a can of paint that's going to last 15 years and they're going to be happy. But somebody else is going to grab a can of paint, it's going to last 6 months and they're going to be mad. And your customer service, like your reputation as a business is going to be in the toilet. So that's one of the reasons why variance is an important thing to look at, is because you're wanting everything to be closest to the average if you're talking about the reliability of a product. And so this company is going to test these paint formulas, these two paint formulas, A and B, to determine which one is the better formula. Maybe it won't last as long on average, but if it's more reliable, it has a smaller variance, then people are going to be happier because you can say what the average is, and when they buy the paint, it can be expected to last about that long. Does that make sense? Okay, so that's why. Okay, what we have is we have two small populations because they are experimenting. They're creating this paint. So this is the only paint that exists that they're testing. We have brand A and brand B. Brand A lasted this long in months. Brand B lasted this long in months. So we're going to make two tables to calculate our data. And we're going to start with brand A. Okay, and so we have to have our data points. We need the average. Oops, sorry, we're doing population. I'm writing the wrong letter. We need our average, which is mu. And then we have to subtract our average from all of our data points. And then we have to square it. And we need those numbers to calculate the variance. And here's why a data table is the best way to do this. So I'm going to write down all of my data points. Okay. N equals 6. I have 6 cans of paint in my population. The sum of all of the x's, I'm going to figure that out so I can calculate my data point. And so when I add all of those together, I get 240. That's all of these x's. And so my average is equal to 240 divided by 6. So the average length that this paint lasts is 40 months. So I'm going to write that on there. Okay. Now, I have to do x minus u, or mu. So 15 minus 40, negative 25. Hit the squared button, 625. Then I do 65 minus 40, which gives me 25. Hit the squared button, 625. 55 minus 40 is 15. Hit the squared button, 225. 35 minus 40 is negative 5. Hit the squared button, 25. 45 minus 40 squared, 25 minus 40 squared. All of these numbers in this column will always be positive. Okay, you cannot get a negative number in this column because you're squaring it, and a square negative times a negative is a positive. So these will always be positive. Then I add them all up. This column, I add it all up. And when I add all these up, I get what's called the sum of x minus mu squared. And that is 1750 in this case. Okay, 1750. Just put it right down there.
Wait, 1750?
Uh-huh. Yeah, 1,750. Okay. Now, The variance is the sum of all of the squares of the differences between the data and the mean divided by the number of data points. I already have this sum because I made this table and I just added up the column. So that's 1,750, and I added up 6 numbers. So the variance is 291.67. This is not close to 0. 0 means it doesn't vary at all, right? So this is varying a lot, probably. Okay, so brand B, we have our data points.
Don't we still need that chart?
Our average. I have it on paper.
Oh.
Our data minus our average, and then our data minus our average squared. Okay, so our data points for brand B, we have a 40, a 50, 35, 40, 45, and 30. Okay, when I add all of these up, I also get 240. So my sum of my x's,
Wait, you add that side on brand B?
yeah, I did it on brand A too. You always add up all your data. This is how you find your average.
Is that how you got the 240?
Yeah.
Okay.
So my average is 240 divided by 6, again, because I added up 6 numbers. And so my average this time is also 40. Okay, so far okay? Now I'm going to, 40 minus 40 is 0. 0 squared is 0. 50 minus 40 is 10. 10 squared is 100. 35 minus 40 is negative 5. Squared is 25. 40 minus 40 is 0. Squared is 0. 45 minus 40 is 5. Squared is 25. And then 30 minus 40 is negative 10. Squared is 100. And when I add all of these together, I get 250. And that means that my sum of x minus mu squared is 250. And my variance, again, is that sum divided by n. So I take 250 and I divide it by 6, and I get a variance of 41.67. Now remember brand A, our variance was 291.67. Which brand, A or B, is a more reliable paint brand? B. Because if it says on average it lasts 40 months, that paint is going to last pretty close to, I mean, it's the furthest it is away from the 40 months is 10 months.
Okay.
You know, so that's the extreme. This paint is going to be closer to the average, so this is the paint that the company would want to go forward with because it will make the least people angry at them and lose them the least amount of money. Right? So brand B is more reliable.
Why is, okay.
Because the variance says how far it is away from the average. And if you're talking about, what they're talking about right here is how long is the paint going to last. And they're saying the average is 40 months. But with brand A, the variance is 291.
And then the variance of that one is 41.67.
Yeah, so that means this paint is going to be closer to the average. So it's going to be a more reliable paint. Does that make sense?
Yeah. So it's a smaller variance, right?
Smaller variance, closer to the average.
The average is 0, right?
No, the average is 40.
Oh, 40.
Yeah, the average is 40 months.
Oh.
And in the case of paint, if you're a company, you tell how long the paint lasts. If I go to the store and I'm looking at gallons of paint and it does not say how long it's supposed to last, I am not buying it because the first rainstorm that comes along, it'll wash off or something. I don't know. They didn't say, right? So you look for something that says, like, lasts In this case, it's saying 40 months. So last 3.5 years on average. So you go, okay, 3.5 years, that's pretty good. I'll buy that paint. But then if you buy the brand, if they used the brand A version, some of it only lasted 15 months. And it's supposed to last 3.5 years. Didn't even last a year and a half. Now I'm mad because this paint that I bought, that I spent all that money on, is garbage.
How long is paint supposed to last?
It depends on the brand.
Really?
25 years.
No, not 25 years. 5 to 10.
Really? 5 to 10?
Mhm. But so when they test the paint, they test the variance for reliability. How close is it to the average? So that if some person goes and buys a random bucket of paint, it's more likely to stick close to the time they said it will.
Not only that, but where you put it matters too.
That is very true. Yeah, if you paint plastic, it's not going to last nearly as long as if you paint concrete.
Now, when it says it'll last that long,
If they had been samples instead of populations, okay? The only difference between the sample and the population, the average is still going to be the same. However, we're going to call it X bar instead of mu. Okay, so average is the same. The number in the sample is the same. Okay. The sum of X minus X bar is going to be the same as X minus mu. Okay? Because remember, the average is the same. We just use a different notation if it's population versus a sample. Okay, so these are equal. Always. This is just sample population. Okay? So the equation, however, has changed. The equation for the variance of a sample, we divide by n minus 1. Okay, guys? Shh. All right, so I'm going to go back and remember that my sum on brand A was 1,750, and my sum on brand B was 250. Okay, the sum is the same. So now my equation does change. So I have 1750 divided by 5 instead of 6. So that gives me 350. And here I have 250 divided by 5 instead of 6, which gives me 50. Now our old numbers were 291 and 4167. These numbers are 350 and 51. Obviously they're kind of far off from the original number with the population. However, the results are still the same. Brand B is more reliable, and the sample would mirror the population.
the 1750, okay.
We take the sum from A here. It's the same table. The table would be exactly the same. The only difference in the table would be instead of a U, we'd have an X bar.
Okay, but it would be the same thing. It would be, or no?
It's the same numbers.
Okay.
The numbers are the same because U and mu and X bar are the same. They're both average.
Okay.
And they're both calculated the same. They're the same. Does that make sense? It's just that this is the average of a sample. This is the average of a population.
Then you took 1750 over 5.
Because it's n minus 1 instead of n.
Oh, okay.
So the 6 turns into a 5.
Okay, I get it. And then 350 and 50 are the answers?
The new variances, yeah.
Okay.
But as you can see, there's still, brand A has a huge variance, brand B has a small variance. So that's, if that was a sample, it's still mirroring the population. Okay, so we're going to do this on a separate paper. because of the fact that it's just so much data. And what we want to do is go ahead and that table I passed out, grab that. Okay. And we have all of these are temperatures in Canadian cities east of Toronto in July in Celsius, not Fahrenheit. And then all of this is rain in millimeters. Okay, we're going to see which is more variable, temperature or rain. Okay, so what we have, it did say that they were populations, so we are using not X bar. So to calculate the average, I take the sum of all of the x's. So I add all of these up, and it's actually, I put it down here, 228.6. Okay. Now I've added up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 numbers. So n is 18. So my average is 228.6 divided by 18. 18?
Yes.
Okay, which is 12.7. Okay, so that's the average is 12.7, so that goes here. As long as you remember, you always have to subtract 12.7.
Yeah, that's what I did.
But remember, guys, I've told you this before. I do all of the steps on the notes because it's notes, right? So somebody has to be able to come back and look at these and make sense of it. Okay, so the average was 12.7. Now, if you have a lovely, lovely graphing calculator, or remember, you can download the Desmos calculator app. Or if you even have, this is not a graphing, it's just a scientific. I take the 11.7 and I subtract the 12.7. Gives me -1. And then I hit the x squared button. 1. I didn't actually have to do that, but you know. And then I do 13.7 minus 12.7, which is 1, and 1 squared is 1. 10.5 minus 12.7 gives me a -2.2. I square it. Ah,
Is that a negative one or a regular one on the second one?
regular. I hit the thing. It's a -2.2. And when I square that, which I messed up right now, so I get 4.84. 14.2 minus 12.7, 1.5 squared. Sometimes it does this. I don't know why.
You can put it into a different program too.
Yeah, I will later. I'll figure it out someday. I'm not really in the mood. So 1.5 and then 2.25. Okay, and I keep going down the list, and I get 1.2 when I subtract, which gives me 1.44.
Friends.
Are we gonna have a home problem like this
Possibly.
as long as this?
Yep. You guys are lazy when it comes to writing.
I mean, not really. I don't even have color class.
Just a little bit.
Just a little bit.
Just a little bit.
I'm gonna. You have your squares. Then I add up this whole list. Okay, and the sum of this whole list right here is 138.6. Right. And then for your variance,
7.7.
you get 138.6 divided by 18. Is it? Yes, it is. So your variance for the temperature is 7.7. Let me write down the correct numbers for the precipitation. So now I subtract 18.6 minus 73.1 and I get negative 54.5. And then I square that. And then I subtract 37.1 minus 73.1 and I get negative 36. And I square that. And I subtract again and I get negative 2.2 and I square that. And then I subtract again and I square. What's the question? Huh?
That was fun. No, like she said, why do I even try?
Oh, no, come on now. I subtract again 15.1, negative 15.1, and then I square that. And then I subtract again negative zero point 0.1, and I square that. Subtract 4.5, square 20.25. Subtract, square, subtract, square. Yeah, negative zero point 0.1. And I keep doing that, subtracting and squaring. Subtracting and squaring. Okay, once I've done all of the subtracting and squaring, again, when you're doing this with the calculator, don't do all of the subtraction and then go back and do all of the squaring. That's going to take you way too long. Subtract. So I'm like the first one. 18.6 minus 73.1 gives me an answer. Square it. Write them both down. Okay, do the two columns at the same time. Subtract, square, subtract, square, subtract, square. Otherwise, you're going to waste a lot of time doing all of the subtraction and then going back and plugging in all those numbers and squaring them. Okay? Make sense? I am the queen of efficiency. This makes sense, I promise. Okay. When you get all of the perfect squares, you add them all up and you get a total. And your total, I didn't total it, so I have to do that. Never mind. 297.3 plus 1296. So I'm going to pause real quick while I total. Okay. So when you add them all up, okay, guys, if this is notes, right? So if you can write down enough that you know what the steps were and then say etc. and then put the total at the bottom, okay? But on the homework, you actually have to do the problem. So the sum of the squares was 16,254.79. So the variance, guys, we divide that by 18. Whoops. And we get 903.04. Okay. Now the question asked us to compare the variance between the rainfall and the temperature. Which one was more variable?
I forgot when this one came from.
The temperature has a variance of 7.7.
Yeah.
The rain has a variance of 903.4. Temperature is more consistent. It doesn't, month to month to month. It's the same. It's more consistent. Rain is all over the place, according to this. Okay? Any questions?